Okay, so the linear momentum conservation principle states that the linear momentum of an object remains constant unless an unbalanced force is applied. So unless a force is applied, Canada, unless an unbalanced force is applied, because now if you consider a teacup or a ball on a table, right, standing stationary, it experiences two forces, right? One is the gravitation force, gravitation attraction force, which is we can phrase as the weight of the object, and also the normal reaction force. So it is experiencing two forces, but they are balanced, equal and opposite. So net force will be zero. So it remains stationary. So we can say momentum is constant. So momentum will be constant at zero. Okay. So therefore we have to mention unless an unbalanced force is applied. Okay. තෝරාගත් දිශාවක් ඔස්සේ අසමතුලිත බාහිර බලයක් ක්‍රියා කරන කල්හි එකී වස්තුවේ ගම්‍යතාව එම දිශාව ඔස්සේ සංස්ථිත වේ. තෝරාගත් දිශාවක් ඔස්සේ අසමතුලිත බාහිර බලයක් ක්‍රියා කරන්නේ නැත්නම් එම වස්තුවේ එම දිශාව ඔස්සේ ගම්‍යතාව සංස්ථිත වෙනවා. Right? Okay. So then we discussed few examples in the last class. Now, for example, if you consider the collision of two blocks, right? The collision of two blocks, we can't consider the linear momentum for each block because during the collision, it experiences a impulse force. Body කාලයක් in very short time, force එකක් react වෙනවනම් අපි ඒකට කියනවා impulse force එකක් කියලා. So there will be impulse force acting on an object during the collision. So it is an unbalanced force. So therefore we can't consider linear momentum conservation for each object separately. But if you consider as the whole system, then the linear momentum is constant. Okay, so if you consider the system, the linear momentum will be constant continue. Okay, so therefore we can consider the linear momentum conservation for the system, not for the individual body. Okay, so we did discuss regarding such collisions in the last class, and also an explosion. Okay, so today we will be discussing about types of collisions. Okay, so mainly there are three types of collisions classified into elastic, inelastic, and perfectly inelastic. Okay, so you can write down the topic collisions. Okay, collisions are classified into elastic, inelastic, and perfectly inelastic collisions based on how energy and momentum behave during these interactions. Okay, so here now today we are going to discuss what is elastic collision, what is inelastic, and perfectly inelastic collision. So those things we will discuss in today's class. Okay, so first write down the topic elastic collisions. Elastic collisions. Okay, so you can highlight and light. These are the collision where both momentum and kinetic energy are conserved. Elastic collision එක ගම්‍යතාව හා චාලක ශක්තිය දෙකම සංස්ථිතිකයි. In elastic collisions, both momentum and kinetic energy are conserved. In a collision, momentum and kinetic energy both remains unchanged. Then we call such collisions elastic. Pratyastha Gato. Elastic collisions. Okay, so in elastic collisions, as I told you, both momentum and kinetic energy are conserved. So this is very important. Like in MCQs and all, they'll ask like true or false statements. They have asked many times like about elastic collision. What is the quantity remains unchanged? Okay. Okay. So in elastic collision, both momentum and kinetic energy are conserved. Okay. So now let's say, for example, we have two masses, one mass m1 traveling with the velocity u1, and another mass m2 traveling with the velocity u2. So the total momentum before the collision will be m1 u1 plus m2 u2. So after the collision, the velocities has changed to v1 and v2. Then we can write the momentum conservation m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Did you understand this equation? Do I need to illustrate with the example? Yarosh, I can't hear you clearly. Can you speak closer to the mic? Okay, actually, I didn't hear anything at all. Or else you can drop a message. I don't know whether it's my connection problem or.
Can you hear me now?
Now fine. Okay, can you?
It would be better if you can illustrate it, sir.
Okay then. So let's say we have two masses m1 and m2. So
Sir,
this is
by the way, if
m1.
you are feeling unwell today, we can reschedule the class
No,
for
no,
another
that's
day.
fine. Today I want to finish this momentum part. I will finish it. It's only like another 40 minutes are there. I can finish it. Okay.
Okay, sir.
Okay. So here let's say the mass m1 traveling with the velocity u1 and another mass m2 and traveling with the velocity u2. Okay. m2 u2. Okay. So if they are colliding means definitely u1 must be greater than u2 according to my illustration, right? So it is there is no any constraints that you want to draw because this is a just algebraic thing just to understand the total momentum before the collision is equals to the after collision. Okay, so let's say this one m1 and velocity u1 and this m2 velocity u2. So this is before collision BC, and after the collision, let's say the velocities has changed to v1 and v2. Maybe that v1 could be in this side or maybe it can be other side. Okay. Uh, so if it's actually in other side, if you solve this problem, you get a negative value for v1. If suppose that v1 is in the other side. Okay. So let's just mark as here v1 and this is v2. So then this is after the collision. So total momentum before collision is equals to total momentum after the collision. Okay. Right. So therefore we can write m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Right. And also the kinetic energy is conserved. That means total kinetic energy before the collision is equals to total kinetic energy after the collision. The before collision total kinetic energy is half m u1 squared plus here half m u2 squared. Right. So the kinetic energy, this expression, can you understand, right? The total kinetic energy before the collision is equals to the total kinetic energy after the collision. Is that clear?
Yes, sir.
Okay. Okay. So in elastic collisions, no deformations occur, or any deformation is temporary. Okay. Now, for example, you can consider a collision between, for example, let's say two tennis balls. Okay, assume the collision is elastic. Now, during the collision, what happens? The ball poddak chappa venani. So it's a deformation, and then after the collision, it will again come to its original uh, shape and size, right? So that's what it says, that the deformation is temporary. Okay. Okay, so we can consider examples: collision between atomic particles. Now, in chemistry, you will study this kinetic theory of gases. So there you consider these gas molecules as uh, tiny particles, point particles, and also you come to a assumption the particles are the collisions between the particles are uh, the collisions between the particles are totally elastic, completely elastic. Okay, they are elastic collisions. Okay, so elastic collision means uh, if I say the word elastic means it is 100% elastic. I mean, there is no partial elastic. Okay, if it's inelastic only, there is a like a fraction we can consider how much of energy is wasted and all. Okay. Okay, so here collisions between atomic particles or gases we can consider as elastic collisions, and collisions between billiard balls, and ideal collision between steel balls. So they are example for elastic collisions. Okay. Now let us try to do an example on elastic collision. So we have a problem. A ball of mass m1, mass 2 kg, is moving with a velocity of 6 meters per second toward a stationary ball of mass 3 kg. After the collision, the two balls move along the same line. Find their final velocities v1 and v2. Okay. A ball of mass 2 kg moving with a velocity of 6 meters per second towards a stationary ball. Okay. After the collision, the two balls move along the same line. Find their final velocities v1 and v2. Okay, since the collision is elastic, we can write the conservation of momentum. So the conservation of momentum we can use for all the collisions, not only for the elastic collisions. For the inelastic collisions also, we can consider the momentum conservation. Okay, so apart from that, uh, okay, so we can substitute the values here. So the mass is 2 kilogram, velocity is 6. The other mass is at stationary, so velocity is 0. And 2 times v1 plus 3 times v2. Yes, 2 is the mass of the first particles, 3 is the mass of the other particle. So we get one equation that 12 equals 2v1 plus 3v2. Okay. Okay, and also we can write the conservation of kinetic energy. So the total kinetic energy before the collision is equals to total kinetic energy after the collision. So total kinetic energy before the collision, here we can substitute the values. Half into mass is m into v squared, and the other particle, the 3 kilogram, is at rest, so kinetic energy will be 0. And after the collision, the kinetic energy of the 2 kilogram will be half into 2 into v1 squared, and the 3 kilogram is half into 3 into v2 squared. Okay, and then we can simplify this. Here 2 and 2 cancel, 6 squared 36 equals to v1 squared plus 3 over 2 v2 squared. So we have two unknown variables v1 and v2, and also we have two simultaneous equations. So we can solve this simultaneous equation to find the solutions for v1 and v2. Okay, so let us try to solve this equation. So first I'll note down the two equation here. 12 equals 2v1 plus 3v2, and the other equation is 36 equals v1 squared plus 3/2 v2 squared. Okay, so these are the two equations that we have to solve. So now from this equation 1 I can subject v1. So v1 is equals to 12 minus 3v2 divided by 2. So now I can substitute that in the equation 2. So substitute in the equation 2. So we have 36 equals to 12. So here 12 and 3, the 3 is common, so I can take that out. 3 times 4 minus v2 over here 2, the whole thing squared. v1 squared plus 3/2 v2 squared. Now let's simplify this. 36 equals 3/2 squared, 9/4, 4 minus v2 squared plus 3/2 v2 squared. Now I can multiply both sides by 4 and divide by 3. Okay, I multiply both sides by 4 and divide by 3, which means multiplying by 4/3, right? So here if I multiply by 4/3, 4 into 36 divided by 3 will be 12, and here 4 and 4 cancel, 9 divided by 3 is 3, and let's expand this bracket. 16 minus 8 v2 plus v2 squared plus multiplying by 4/3, so 4 and 2 cancel, 2 will come, 2 v2 squared. Okay, now we'll simplify this. 4 into 12, okay, I think 4 into 12 plus, so here 3 into 16 minus 8 into 3 is 24 v2 plus 3 v2 squared plus 2 v2 squared. Okay, I think 3 into 16, 3 into minus 24 v2 plus 3 v2 squared is 2 v2 squared. Okay. So now we'll take all the terms to the right and simplify. 5 v2 squared minus 24 v2 plus 3 into 16 is 48. 4 into 12, 48 minus 48. So we have 0 equals 5 v2 squared minus 24 v2. So v2 is common, we can take that out, v2. Then we have 5 v2 minus 24. Okay, so we have a product is equal to 0, therefore the solutions are v2 equals to 0 or 5v2. 5v2 equals 24. So v2 equals 4.8.
It should be minus 24, right?
Sorry?
Uh,
Yeah. I took the minus 24 to the other side.
Okay, sir. Okay.
So, yeah. And then dividing by 5 will be 4.8.
Okay, sir. I got it.
Okay. So then we have V2 two solutions. One is V2 equals 0, and then V2 equals 4.8 meters squared. I think I missed with the, okay. So we have taken V2 as, okay. Now, let's say we have two balls. One is, okay, mass is 6, right? No, 2 kilogram, 2 kilogram. So this is 2 kilogram coming with the speed 6 meters per second. And here the other one is stationary 3 kilogram. This is before collision. And then after the collision, what happens? Now, so this is 2 kilogram and the velocity v1. v1 can be in this direction or in this direction. That depends on the value of v1 that we are going to find. Just for the moment, we will mark here v1. Okay. So it has some velocity. And then the 3 kilogram, if you take, now it has two solutions for v2. v2 we have considered in this direction. So it has two solutions. One is for v2 equals 4.8 meters per second, and the other one is 0. I thought 4.8, okay, that is reasonable, we can take. But if you're taking v2 equals 0, that means after the collision, this ball is not moving at all, right? Can it be a reasonable solution?
No, sir.
V2 has to be 0 means there shouldn't be any collision between these two particles. If the 2 kilogram mass somehow uh, invisible and uh, it it becomes invisible and penetrates through this 3 kilogram. Yeah, it just penetrates through this 3 kilogram. Then V2 is possible. V2 equals 0. But anyhow, it's making a collision, no? Right? So if we take V2 equals 0, that is contradiction for the fundamentals of collisions. So therefore, we can't take V2 as a solution. Okay, so therefore, therefore we can't take V2 equals 0 as a solution. Therefore, the answer is V2 equals 4.8 meters per second. So now taking this value, we can find the value of V1 from this equation here. So the V1 is equals to 12 minus 3 times 4.8 divided by 2. So V1 is equals to, I divide both by 2, so here 6 minus 3 into 2.4. So V1 is equals to 6 minus 3 into 2.4 is 7.2, no? I'm correct.
Yes, sir.
Therefore, V1 is equals to minus 1.2 meters per second, which means the velocity of this 2 kilogram is in the opposite direction. Understood? Is that clear?
Yes, sir.
Okay. Okay, you can note down.
So I will note down this with the above question later because I couldn't write it.
Okay. Uh, or else you can take a screenshot. You didn't write the question.
Yeah, I
Okay,
missed
then
some points and the question.
yeah, then you take a screenshot and keep. Okay, I'll share the
Okay.
PDF with you so that you can get the question. Okay,
Also,
are you
if
done
you
with the
can,
screenshot?
yes, sir. Or else if you can
Yeah, you
send
can
it.
take another screenshot of the problem.
So I need the whole page, that page, first
Yeah,
page.
yeah, you need the word first page.
Yes.
Okay, then so I will share the PDF.
Sorry, sir.
Okay, so everything you understood, right?
Sorry, sir, I couldn't hear.
Yeah. So I'll share the PDF. You can note down, complete the notes. Okay. So regarding solving this problem, you understood everything,
Yes, sir.
right? Okay. So the answers are V1 is equals 1.2 meters per second. That's, I mean, it's in the reverse direction. Okay. And V2, the velocity of the 2 kilogram will be in the forward direction. Okay, so here why V2 equals 0 is incorrect. Great question. Here's why V2 equals 0 is not valid solution. In a head-on elastic collision, momentum and kinetic energy are conserved. If V2 equals 0, the second ball remains stationary after the collision, which should mean the first ball must maintain all the initial momentum and kinetic energy. However, this contradicts the conservation laws. Okay. Okay, so and then write this important part: behavior in an elastic collision. In an elastic collision, both masses must generally exchange some momentum and energy. Okay, there is some exchange of kinetic energy and momentum in elastic collision. The collision imparts a non-zero velocity to both objects unless the masses are very specific, like m1 equals to m2, where velocities can simply swap. So this is something like you may have seen that what you call Newton's cradle. Newton's cradle have such seen that video of uh, balls colliding.
Sorry, sir, what is that?
Okay, wait, I will show you.
Ah, yes, I have seen this.
Yeah, so this is the if the masses are same, so you can see the momentum is transferred. So the momentum exchange equally. So we can do this with one ball, two balls also. Like if we have only two balls, then the one ball remains stationary, the other one will move. Okay.
Ah, yes.
So can you imagine this with only two balls? If the masses are same, what would
Yes.
happen?
Yes.
Okay. So then when let's say the first ball has velocity of 6, after the collision it will stop and the other ball have get the same velocity and move, right? Okay.
In that Newton's cradle, it's not an elastic collision, right? Is it?
Now, which it is like very close to elastic collisions. Okay.
Okay.
But 100% elastic collisions are not there, right? So elastic collision is actually it's a approximation for real world problems, because in real world there is no any such thing 100% elastic. There would be some energy loss due to sound, noise, and all, right? Okay. So it's here we study it's a mathematical modeling. So in elastic collisions, the kinetic energy will remain constant. Okay. So the next type of collision is inelastic collision. So these are collisions where momentum is conserved but kinetic energy is not. So elastic means kinetic energy is constant. Inelastic means kinetic energy is not constant. Some of kinetic energy is converted into other forms of energy such as heat, sound, or deformation. Okay. So the momentum remains constant and kinetic energy not constant. The final total kinetic energy less than the initial kinetic energy. Okay, because there is a energy loss during the collision. Deformation occurs, but object might not stick together. Okay. Example: car accidents where vehicles deform but do not stick together. Clay balls hitting a wall and bouncing back partially. No. Okay. So these are inelastic collisions. Okay. So in inelastic collision, simply kinetic energy is not concerned. So in real world, all the collisions are inelastic because there is no 100% elastic collision. Okay. Okay.
What about in space?
In space also, now if we consider two particles collide, for example, yeah, wait, what happens in space? In space, it cannot propagate the energy as sound, no, right? Because there is no particles to carry out the sound energy in space, right? But the acoustics might be there, the vibrations, the the particles could, I mean, the particles that make up the material could have a high get vibration, so it could vibrate with higher vibrations. Now normally if you take a solid in a crystal, it is have a small vibrational motion, right? So during the collision, what could happen is that the sound is because of the acoustics. When we hit two objects, so that acousticity could make the particles more vibrations. So again, in space also we can find 100% elastic collision. Okay, so I mean, there is no 100% elastic collisions. Now, in kinematics also, we consider the molecule or gas molecules collisions are elastic, but it is you study under the assumptions you made, no, under the
Yes,
kinetic theory.
yes,
Yeah. So the examples you can note down: car accidents and where vehicle deform but do not stick together. Clay balls hits a wall and bouncing back partially. In fact, if you take a tennis ball also, that is also in elastic collision. Okay, because you, for example, let's say there are two. Uh, wait. Uh, okay, so let's say there are two walls. Okay, there are two walls, and then we hit with a tennis ball. So if we hit with the tennis ball, it impact with some velocity, let's say 12 meters per second, and then again it will comes in such a path due to the gravity. And if this collisions is elastic, then it also should rebounds with the same speed. So then it has to be rebounds with the same speed. But in real, no, right? It will have some less speed. After each consecutive collisions, the velocity as a fraction, small, tiny amount, it will decrease, no? Okay,
yes,
because there is noise, sound is coming up, right? When you hit the tennis ball to the wall, so if it's elastic collision means you shouldn't hear any sound. There shouldn't be any sound. Understood? Because the total kinetic energy should remain constant. It's elastic.
yes,
Okay. So the next type of collision is perfectly inelastic collisions. This is a specific type of inelastic collisions where the colliding objects stick together after the collision. So highlight stick together after the collision. Okay. Perfectly inelastic collisions. Where the colliding objects stick together after the collision, moving with a common final velocity. And in perfect inelastic collision, the kinetic energy loss is maximum. The loss of kinetic energy will be maximum in perfectly inelastic collisions.
So I will write the note after class so we can
Yeah,
continue with
sure.
the.
Okay. So here also we can consider the momentum conservation. The momentum is conserved for all the collisions. Okay. Now here, if you consider the let's say two masses M1 and M2 colliding, so the momentum is not constant to this mass M1, and also it's not constant to this mass because during the collision it will experience a unbalanced force. But as a system, no matter whatever the type of the collision is, the that forces impact forces will be internal pairs to the system. I think that video is some video is randomly in background. Okay. So therefore, the momentum is conserved quantity for all type of collision. Is that clear?
Yes,
So these are the questions they will ask in that true or false question. When you do past papers, you will see in many occasions. Okay. So momentum is a conserved quantity for all types of collisions. Okay. Okay. Have you read this book, 2001 Space Odyssey by Arthur C. Clarke? Give me a second.
no, sir, but I have it.
Have you read that Arthur C. Clarke's 2001 Space Odyssey?
Not yet, sir, but I have the book. I read
I think
that.
for a sci-fi book, I think the best one I could recommend is 2001 Space Odyssey. There are some interesting phenomena that was written by Arthur C. Clarke in 1960s, I think, right?
Yeah,
So that time, like he has mentioned about that artificial gravity and everything. Uh, so it's really interesting book. I mean, but well, after your exams, you better read that book.
yeah, I read that his book called Rendo with Rama.
Uh,
I couldn't read the other one yet.
uh Okay. Uh, yeah. So there he has discussed like many concepts like hybridize that hy- hibernation sleep and a lot of things, lot of that. So those who are reading that book in 1960s, it's like a scientific fiction. But now most of the things they are actually come to real life. So it's really interesting. Now in fact, the satellites. If you, I mean, it's already you may have studied in your primary grades. I think that satellite is also a concept of Arthur C. Clarke. He is the one first
Yes,
who predicts that we can make things orbit around the Earth. Okay, then so perfectly inelastic collisions. Okay, why I suddenly this thing came to my head is because I'm talking about the momentum conservation now. So there is a one thing called such a thing like uh, let's say there is a planet. Okay, that planet is rotating in some direction. Let's say so. Let's say this is the axis the planet and it's rotating orbiting rotating. Okay, so when there is a rocket or space shuttle passing through this, okay, so they will come with the engine shut. So let's say it comes with the engine on and then they shut the engine, so it will move with the constant velocity, right? So after that, due to this attraction, it will be move toward that, but again still this space shuttle have larger speed, so that speed is enough to pass over this planet's gravitation. So what they have to do is when they pass the planet, they quickly turn on the engine. They suddenly turn on the engine, which means they make a like an explosion. For example, in explosion, what happens? There will be like making into two pieces. Then the after the explosion, the velocity of each part will be high. No, so what happens is they can use this some conservation of this planet, and then they gain some velocity, larger velocity, because and this planet will lose some momentum. This will get large some momentum, and the planet will lose some momentum. But for the planet, it will be very negligible because it has a very large mass. So such thing and all I studied. I mean, after reading such, uh, books, and that thing also actually possible. Did you understand what I was saying?
yes,
Okay. So perfectly elastic collision here, the uh, kinetic energy loss is maximum, and then objects stick together after the collisions. Okay. Okay. Let's do this question for the practice. 5 kilogram ball slides on a frictionless surface at 10 meters per second in the horizontal direction. 5 kilogram moving in this direction with a speed of 10 meters per second. It strikes stationary 3 kilogram ball after the strikes a 3 kilogram stationary ball. 3 kilogram, velocity is 0. So this just movements before collision. And after the collision, the 5 kilogram ball moves at 6 meters per second at an angle 30 degrees below the horizontal. See, 5 kilogram in this speed 6 meters per second, angle 30 degrees below the horizontal. Okay. Find the velocity and the magnitude and the direction of the 3 kilogram ball after the collision. So then I draw this 3 kilogram. Let's mark the speed v and make angle theta. Okay. So the momentum is a conserved quantity of the system. So therefore we can consider the linear momentum conservation. So using linear momentum conservation principle. So we had the momentum is a vector quantity, so therefore we had to consider direction. So I consider horizontal to the right. So total momentum before the collision is 5 into 10 plus 3 into 0 is equals to, now this one I resolve into this direction, 6 cos 30, and this is downward 6 sin 30. This one is v cos theta and this one is v sin theta. Okay, so before collision we have in the horizontal direction only this one, and after the collision we have 5 kilogram moving to the here 6 cos 30, 5 into the horizontal direction we have 6 cos 30 plus 3 into v cos theta. So here 5 into 10, 50 equals to 5 into 6 into cos 30 is root 3 over 2 plus 3v cos theta. 2 and this 3 cancel. So we can take this to the other side. 15 minus 15 root 3 equals 3v cos theta. This is equation 1. And then I can consider the vertical direction. I can consider the vertical direction. Initially in the vertical direction there is no any velocity, so initially 0, right? This one also have no any velocity or momentum in the vertical direction, and this anyway stationary. Is equals to, and then here we have vertically upward 3 into v sin theta minus 6 5 into 6 sin 30. So then I can simplify this here. 3v sin theta equals to 5 into 6 into sin 30 is half. So here 2 and then this cancel 3 and this 3 and this 3 cancel. So v sin theta equals to 5. Okay. Okay, then I can take this as equation number 1. And then 1 divided by 2. So 1 divided by 2 we have v sin theta divided by 3v cos theta equals to 5 over 50 minus 15 root 3. So V and V cancel. Sin theta divided by cos theta is tan theta. 3 into 5, 15 here, divided by 50 minus 15 root 3. Okay, so let us simplify this. We can divide all by 5. So tan theta equals to 3 over 10 minus 5 root 3. Okay, so that is tan theta. So then we have to get the sine theta and the cos theta. Yeah, we can find, but here this is not so, or else we can do like this. Now, use this space here. So tan theta is this, so we can take a right angle triangle. Theta, tan theta is equals to opposite over adjacent. 3 over 10 minus, so 10 minus 5 root 3. So then we have to find this x, the hypotenuse. So therefore x squared is equals to okay, so here x squared is equals to 3 squared plus 10 minus 5 root 3 squared. So x squared is equals to 3 squared 9, 100 minus 15 to 100 to 10, 2 into 10, 20, 20 into 5, 100 root 3 plus 25 root 3. So we have x equals 109, 109 plus 75 root 3. Or shall we simplify and get the value in angles? Right. So this is x. So therefore sine theta is equals to opposite over hypotenuse. Not 65 degrees. Okay. Or else I simplify in this method. Okay.
I use
Now
tan
here,
inverse and got the answer.
yeah, what is the angle?
65 degrees, 53 minutes.
65 degrees, 53 minutes. Okay. So then from we can find the sine value and cosine value for this. Okay, I will do the same question in another way. Okay, so here we have v cos theta as 50 minus 5 root 3 divided by 3. And then v sine theta is equals to 5. So then here what I'm going to do is I square these two terms and add. So v squared cos squared theta plus v squared sine squared theta is equals to, so here 50 minus 5 root 3 over 3 squared plus 5 squared. So then here we can take v squared and cos squared theta plus sine squared theta is equals to then square this. So 50 squared is 2500 minus 15 to 200, 100 into 5, 500 root 3 plus 25 root 3 squared, then it will be 3. 25 into 3 over 3 squared is 9 plus 25. So here we get v squared is equals to, because is equals to 1. So LCM 9. So here we get 2500 minus 500 to 3. Here 25 into 3 and here 25 into 9. We get 25 into 12. So when you simplify this, you will get two values for v actually. Okay. $25 to 12, how much? 25 to 10, 2500, 2550, 2550. So we get 5050, no? Get this term and this term. So v equals to, v squared is equals to, you got plus or minus. Okay, so if you simplify this, you get, okay, wait, 25, 25 into 12. So 25 into 12, 3000, 300, 300. So 2800 minus 50 root 3 divided by 9 square root. So 2800 minus 50 into root 3 is 1.732 approximately, and then that number should divide by 9. 303. Root 3 is 1.73, no? 2,800 minus 50 into 1.732. 1.73. This number divided by 9. Divided by 9. Here it should be 500 root 3. I'm using 50 root 3. Sorry. Yeah. So 2,800 minus 500 into 1.73 divided by 9. 250. So approximately 215. So 250 square root 14.66. Okay, so you also got well. Okay. So therefore we get V equals plus or minus 14.66 meters per second. Okay, so here then angle is this one, theta value is this, and V is so here we have to consider uh, V has to be plus value. Okay. Now here the first easy way is considering the vertical component, we got this one V sine theta equals 5. Okay, V sine theta equals 5. That means if you solve the vector, so this component is 5. So this component is value is 5. Okay. Then now we know the angle, you can use the angle here and then you can find straight away the V value. So here for V, we have to take plus 14.66. Minus means it will be in this direction. It contradicts. Okay. Because if you take to this direction, then components are in this side and this side. So this one has momentum in this side. There should be a momentum cancelling that, because initially the total momentum in the vertical direction is 0. So therefore the total momentum in the vertical direction must be 0 for the whole system. Did you understand? Hirosh? Okay. So I think with this we are done with the theory part of the momentum. So I'll share you some questions from momentum. Here I can find. So I think these are the questions. I think these are past paper questions. Here, from here we have momentum concept, linear momentum. So some questions are past paper here, 2002. I'll share you this. You can do this question, and also I'll share you this. So this is, you can find, yeah. Momentum conservation, center of mass and collisions. So this is actually from objective physics. So objective physics is a book where there's even university lectures refer. In fact, our papers are made by university professors. So they also refer this objective physics book. They recommend this book. So I'll share you this also. You also can do some questions.
Okay. Thank you, sir.
And our next topic is movement of force. Okay, I will share you a small recording about half an hour recording about a movement of force. It's only the basic the conceptions are there. So you can go through that, and then we can continue from there. Okay. Okay then. So I'll wind up the session.
Okay, sir. Thank you, sir. Good night, sir.
Okay. Good night.
Get well soon, sir.